Welcome back. During this lecture, we'll be examining the development of great Roman structures that use the arch as a principal structural element. We'll see how the arch was integrated into these structural systems and how the structural systems in turn were influenced by the unique structural characteristics of the arch. Now, when I think of Rome, the first image that comes to mind is an arch. And I don't think that's just because I'm an engineer. While the Romans probably borrowed this technology from their Etruscan neighbors, the arch has come to be closely associated with many characteristic aspects of Roman civilization. It's present in bridges that carried the famous Roman roads to the far-flung corners of the empire. It's present in monumental aqueducts that brought fresh water to the cities and in the sewers that carried away the effluent. It's there in the triumphal arches that celebrated the victories of the legions, and in the city gates that kept enemies at bay. Arches circumscribed the Colosseum, providing convenient public access to the spectacle of the day. And in the form of vaults, they enclosed grand baths and basilicas, public gathering places that provided for the needs of the people while reinforcing the Roman political and social order. But the arch wasn't just present in these structures, it enabled them. In earlier civilizations, the principal technology for spanning long horizontal distances was the beam. And as we've seen, the length of a stone beam is fundamentally limited by the need to span that full distance between supports with a single stone, and by the low tensile strength of that material. But the principal structural characteristic of an arch is that it carries load entirely in compression. So as a result, the span isn't limited by the low tensile strength of the material, or by the sizes of the individual stones that make up the element. It can be built up of many, many smaller stones or bricks, like my model here, and as a result, greater spans are possible than could even be conceived of with stone beams. As a result, the Romans' use of the arch opened up a whole new realm of structural possibility. But an arch can only carry load if it's adequately supported. The critical requirement for the stability of an arch is its lateral restraint. As you remember from Lecture 8, under load, an arch has a natural tendency to flatten and to spread out laterally. That lateral spreading of the bases of the arch is called thrust, and thrust must be resisted. It has to be restrained by some sort of physical device, by some physical mechanism that supports and prevents that lateral movement of the bases of the arch. On my model, that support is provided by these two wooden blocks at the base. And as we know, if those blocks are removed, like this, the arch is no longer capable of carrying any significant amount of load, as you can clearly see here. With that little demonstration as review, now let's begin our study of Roman arched structures with one that we've already encountered in a previous lecture, the Pont Saint-Martin, a beautiful stone bridge constructed in northern Italy in the 1st century BC. Now this is just about the simplest form of arch structure one can possibly imagine. A single semicircular arch supporting a single-lane roadway. Yet this 103-foot span is actually among the largest of any Roman arch that survived from antiquity. So let's examine the structural system of the Pont Saint-Martin. We'll begin by constructing the bridge virtually using this 3D computer model as a way of identifying the main structural elements in this bridge. First, these foundations are cut into the rocky slopes of the riverbanks and then reinforced with stone masonry. The foundations provide both vertical support to hold the bridge up and lateral support to resist the thrust. Note that a steep river valley is actually particularly conducive to this type of support because the steep bank provides something for the arches to react against. Now we add these two stone projections just above the foundations on either side of the arch. These are ledges that were actually used to support the temporary wooden centering that was used to hold the arch up during construction. It's quite noteworthy that these ledges were actually engineered right into the structure of the bridge, clear evidence of a skill that even modern engineers often find challenging, accounting for constructability requirements while the project is actually still being designed. Now we add the single stone arch ring, which extends across the full width of the bridge on top of the centering, and then once the arch is in place, it becomes self-supporting and the centering can be removed. On top of the arch ring are two spandrels. These are stone walls that form the sides of the structure. Next, we fill this entire space between those two spandrels with concrete. And finally, we add the road surface, which the Romans called pavimentum, a layer of granular material like crushed stone and tile mixed with lime or cement. So now that we've identified the principal elements of this structural system, let's figure out how it works. By following the load path, starting at the point of application of the loads and following it all the way down to the structural foundations. The principal live loads acting on the structure are pedestrians, vehicles, and snow accumulation in the winter. Let's start with a snow load, which would typically be uniformly distributed along the full length of the bridge. The snow's weight is applied to the road surface and then transmitted down through that concrete fill to the main arch ring. And then the arch ring then works exactly as we saw in Lecture 8, transmitting internal force in axial compression all the way down through the individual voussoirs out to the foundations. The pedestrian and vehicular loads aren't quite so simple. As we've seen, an arch is best suited to carry uniform loading, like snow load and the bridge's self-weight. But pedestrians and vehicles are concentrated loads. They're applied at discrete points along the length of the roadway. And, as we know, concentrated loads tend to cause instability in an arch. The worst case situation involving concentrated load applied to an arch occurs when a very large concentrated load is applied precisely at mid-span, like this. If the magnitude of that concentrated load is relatively small in comparison with the self-weight, well, then all's well. But as the concentrated load gets larger, as you can see here, the shape of the thrust line changes. It tends more toward a triangular shape. And as the thrust line moves progressively closer and closer to that lower boundary of the arch tends toward greater and greater instability. When the thrust line reaches the outer edge of the arch, we're going to see a tendency of the outer ends of the arch to bulge outward. And when that bulge occurs, the arch will become unstable and it will collapse. Just like this. So how did the Romans handle that concentrated load applied to the arch and the instability that results? Well, the structural system of the Pont Saint-Martin actually has a very effective mechanism for preventing this failure mode. Those roughly triangular-shaped masonry walls built on top of the arch rings, the elements we call spandrels. And if all's well, our crew here at the teaching company should have the arch rebuilt by now. And there it is. Who says you can't find good help anymore? So let's see how these spandrels work. Here they are, and all we need to do is put them in place on the arch, which has already been rebuilt for us. And you can very clearly see that at this point, that failure mode, which consisted of the outer ends of the arch bulging up and outward in response to the concentrated load in the center, is virtually impossible now. The spandrel preserves the shape of the arch so that when we press down, that bulging can't occur. And, by the way, the spandrels also have considerably more weight out here near the ends of the span where that additional stability is needed to keep the bulging from occurring. So the system is simple, yet it works extraordinarily well, as evidenced by the excellent condition of the Pont Saint-Martin 2,000 years after it was built, and many more structures very much like it. Now let's visit another Roman bridge, which is actually a few decades older than the Pont Saint-Martin, but adds a few new structural features that we haven't had a chance to look at yet. It's called the Pons Fabricius, located in the heart of Rome, connecting the east bank of the Tiber River to an island out in the middle of the river. It was built in 62 BC, and as such, it is the oldest fully intact Roman bridge in Italy. The structural system of the Pons Fabricius is essentially the same as the Pont Saint Martin, except that there are now two main arches. In the Pons Fabricius, the outer ends of each arch react against the foundations on the riverbanks, just as we saw at the Pont Saint Martin, but now the inner ends of the arch are supported in part on that large pier in the middle of the channel. Now I say in part because the inner ends of those arches also support each other. Let's draw a free body diagram to clarify this point. We'll start with the two individual arches isolated from their surroundings. Note that each support has a pair of reactions, one upward and one inward, just as we saw back in Lecture 8. Now let's examine that pier in the middle of the river. Here's the body, which is the starting point for our free body diagram, but what forces act on it? Well, remember Newton's third law. For every action, there's an equal and opposite reaction. So the arch reactions can be just flipped around and applied as loads on the pier, just like this. We know the pier is in equilibrium, so in the vertical direction, there must be an upward reaction down at that bottom surface where the pier rests on the riverbed, which is counterbalancing the two downward forces that are delivered to it by the two arches. But in the horizontal direction, notice that the pier is already in equilibrium. The horizontal reactions from the two arches, when we flip them around and apply them to the pier as loads, oppose each other, and so in effect, they cancel each other out. The pier doesn't need to resist any horizontal thrust because the two arches support each other laterally. This is a fundamental characteristic of an arcade. That's an arrangement of multiple arches placed side by side. The outward thrusts of adjacent arches counteract each other, and as a result, interior arch supports typically don't need to be as substantial as the supports that we see on the outer ends of the arcade. So you may be wondering then why the central pier of the Pons Fabricius is so massive. Clearly the pier doesn't need to be all that massive simply to support the arches, but it does need to resist water pressure in a flood. We know that flooding was a major factor in the design of this bridge because of that small arched opening right above the central pier. No, it's not there just because it looks cool, though it certainly does look cool. It's there to provide a channel for water to pass through during flooding. This opening significantly reduces the water pressure on the side of the bridge, and so significantly reduces the likelihood that that structure will be washed away in a flood. And once again, the system works. The Tiber has flooded many times since 62 BC, and the Pons Fabricius has handled the pressure without complaint. Now, if two arches are good, then 64 arches must be really good. We've journeyed now from Rome to southern France, where we find the magnificent Pont du Gard aqueduct. Built in the 1st century BC, it's over 900 feet long and 160 feet high. And as you can see in this video, the lowest level of the Pont du Gard carries a roadway across the Gardon River Valley, but its most important function is up there on the top level, the water channel that formed a critical link in the 31-mile aqueduct system supplying over 9 million gallons of water per day to the city of Nîmes. All three levels of the Pont du Gard are wonderful examples of arcades, a row of adjacent arches. And as you can see, those arches are constructed entirely of stone, with individual blocks fitted so closely that no mortar at all was required to hold them together. Here's a free body diagram of the first level of the Pont du Gard, isolated from the rest of the structure. And as the diagram shows, the bases of the interior arches have only vertical reactions because the adjacent arches cancel each other out, and as a result, no horizontal thrust remains at those intermediate supports. But the outermost arches still generate a horizontal reaction and must be laterally supported with substantial foundations built into those riverbanks. Now, if you love the Pont du Gard, you'll love the Roman aqueduct at Segovia, Spain. Built around the year 100 AD, the Segovia Aqueduct isn't as tall as the Pont du Gard, but it's considerably longer, 167 arches in all. Its most salient feature is the placement of those arches on tall, slender stone columns, giving the entire structure an almost impossible lightness. This structure dramatically demonstrates that within an arcade, the lateral thrust of each interior arch is counterbalanced by the adjacent arches, even when the arches are supported on tall columns. But what would happen if we elevated a single arch on a pair of columns with no adjacent arches to counterbalance the thrust? We see this arrangement, for example, in triumphal arches, like the Arch of Titus in Rome, constructed in 81 AD to commemorate the Emperor Titus's successful suppression of the Jewish revolt 12 years earlier. Let's see if we can't build a model of this great structure and see how it works. We'll start by building two columns, just like the columns that support the Arch of Titus, and we'll build them out of a series of stone blocks. Now, just as we saw in our Roman bridges, we have two ledges or shelves that are actually built into the structure specifically for the purpose of holding the wooden centering to be used as the support for construction of the arch. And now we can construct the arch proper by adding our stone voussoir all the way up the side of the centering until we're ready to place the keystone in the middle. Now we have the complete arch and we're ready to remove the centering. For some reason it's a little harder to remove the centering in this configuration than it was when I built the arch down on level ground. What's going on? What's interesting here is that the arch is standing up. It's stable. But the difficulty I had in pulling out the centering resulted from the fact that the arch is already starting to sag in the middle. The ends are trying to push outward, as they always do, but because now they're standing on tall columns, the lateral thrust of the arch is actually tending to tip the columns outward slightly. That causes the arch to flatten, and that's the reason there was less space between the arch and the centering, and it was more difficult for me to pull it out. What that would suggest is that this arch is probably not capable of carrying very much load. It's actually probably pretty well through the process of failing due to instability. And so if I add just a little bit of additional load on top, it may very well collapse. Let's see how that works. Indeed it did. Very clearly, when a single arch is placed on top of two columns, the outward thrust of the arch tends to cause those columns to overturn. Let's use the principle of equilibrium to investigate this instability. This is a free body diagram of a single column from the model that I just used in my demonstration. The forces acting on it are the vertical reaction from the arch, which is oriented downward, the horizontal thrust of the arch, which is oriented laterally, and of course the weight of the column. These loads generate two reactions at the base, one horizontal, one vertical. But why have I positioned these reactions at the lower right-hand corner of the column? Well, let me use a model to explain. Let's actually reconstruct one of those columns. Just use a stack of our stone blocks here. And note that we're modeling the condition of the column at the instant before it overturns. And notice that at that instant, just before it overturns, the entire weight of the column is balanced on this corner, the one that's on the bottom side and opposite the direction of the application of the load. And that's why both the vertical and horizontal reaction are concentrated at that point. Now, at this point, I could use equations of equilibrium in order to solve this problem. Write the equation of equilibrium for the sum of moments about this point, and then solve for the unknown thrust applied up here at the top, and then use that as the basis for figuring out what we might have to do in order to stabilize the column. But rather than using an equation, I'd like to actually use the model itself to talk about how equilibrium works in this situation. In this situation, where the column is just on the verge of tipping over, it's useful to think in terms of two different moments acting on this body. The first of those is an overturning moment. Now remember what a moment is. It's a tendency of a force to cause rotation, and it's calculated as force times distance. So the overturning moment associated with this column is the moment caused by the lateral thrust, tending to tip the body over, and the magnitude of that moment is force times distance. So it's the magnitude of the lateral thrust multiplied by the perpendicular distance from the line of action of that force down to the point that we're summing moments about. That's just the height of the column. Okay, so the overturning moment is thrust times height, and it's tending to rotate the column in the clockwise direction from your perspective. There's another moment acting on the column, though, and that's a stabilizing moment, one that's preventing it from overturning. That stabilizing moment is associated with the weight of the body, which I'll represent by simply placing a force up here. The stabilizing moment, again, about this point, is simply this force, the weight of the body, multiplied by the perpendicular distance from that line of action to the point I'm summing moments about. And that perpendicular distance is just 1/2 of the width of the column. So the stabilizing moment is weight times half of the width. The overturning moment is thrust times height. What we want to do in order to make the column as stable as possible is to minimize the overturning moment and maximize the stabilizing moment. How can we minimize the overturning moment? Well, we can't change the thrust. It's associated with the arch. The arch is what it is, and so we can't control it. But we can certainly control the height. So if thrust times height is to be minimized, one way to do that is simply to make the column lower. So we can make a column more stable by making it less high. The other way to stabilize the column, of course, is to maximize the stabilizing moment. That's weight times half the width, and therefore we can maximize that quantity by either increasing the weight or by increasing the width. So in summary, we have 3 different potential ways to stabilize a column that's being acted upon by the lateral thrust of an arch that's resting on top of that column. We can either make the column shorter, or we can make the column heavier, or we can make the column wider. And amazingly, the Arch of Titus exhibits every one of these characteristics. The piers are wide, they are heavy, and they're relatively short, at least in comparison with those incredibly tall, slender columns in the Segovia Aqueduct. And in addition, there's another layer of stone placed above the piers in order to further increase stability by adding even more weight to the columns. Roman engineers didn't know the principle of equilibrium, but their structures suggest a keen qualitative understanding of both equilibrium and stability. Now, once the arch had proved itself as an effective way to span horizontal distances, it wasn't long before it was adapted to the purpose of enclosing space. When an arch is extended to form a roof or a ceiling, it's called a barrel vault, shown here. A barrel vault carries load exactly the same way as an arch does, and it requires the same sort of lateral support for stability. Like the arch, the vault is not a Roman invention. There's archaeological evidence that ancient Sumerians, Egyptians, Greeks, and Etruscans all used them. But as with arches, the Romans exploited the possibilities of this structural form like no one before. The most famous vaulted structure in Rome is the Flavian Amphitheater, also called the Colosseum, built during the period 70 to 80 AD. This video will give you some sense of the extraordinary scale of this structure. Viewed from above, as you see here, the Colosseum is an ellipse, measuring over 600 feet by 500 feet. It probably seated 50,000 spectators. Its height is the equivalent of a 16-story office building. And this intricate layout of entrances and passageways and stairways and all those chambers down below the floor of the arena that are now exposed to the open air are masterpieces of architectural design. From an engineering perspective, the fundamental structure of this building is a series of 80 barrel vaults arranged radially around the first level. These form the main entrances to the amphitheater and also the foundations on which those upper arcades and the concrete seating area were supported. Like the arcades of the Pont du Gard, the barrel vaults of the Colosseum support each other laterally. But unlike the Pont du Gard, the vaults require no additional external lateral support because they're arranged around the perimeter of an ellipse. Every arch is laterally supported by the arch on either side of it. There are no ends in the arcade. Perhaps the most surprising aspect of this building is that it's structurally unremarkable, at least in historical context. The spans of these vaults are not particularly large, and all other aspects of the structure reflect techniques and technologies that were quite well established at the time. In a paradoxical way, this says a lot about the advancement of Roman construction technology. Compare the Colosseum with, say, a theater of the classical Greek era. The seating areas of these Greek theaters were built down into a curved hillside because the Greeks' beam-on-column construction wouldn't have been practical for a building on the Colosseum's scale. That this monumental structure, the Colosseum, the model for all modern stadiums, could be built with no significant technological innovations suggests that the Romans have come a very long way since the 4th century BC. The only truly novel aspect of the Colosseum was actually the unique rope and canvas awning that was stretched over the seating area to provide shade for spectators. But we'll save our discussion of this feature for our lecture on tension structures. Now, if the Colosseum was structurally unremarkable, then the Baths of Caracalla represent the polar opposite. Built as a palace for the people in the early 3rd century AD, the Baths of Caracalla were built on a scale that wouldn't be exceeded until the late medieval period. This vast complex included a double pool tepidarium, that's the medium temperature bath, a circular domed caldarium, the hot room, and that caldarium was only slightly smaller than the Pantheon. 2 gyms for exercising, and a swimming pool with bronze mirrors mounted overhead to direct sunlight into the room. Many rooms had large glazed windows to retain hot air and to use the greenhouse effect for heating. The entire building was elevated on a 20-foot raised platform to accommodate furnaces, hot air ducts, and water distribution. At the heart of this complex was the frigidarium, the cool water bath. At 79 feet wide, this cavernous hall was nearly twice the width of most Gothic cathedral naves of 1,000 years later. The 108-foot height of its vaulted ceiling was only exceeded by the ill-fated Beauvais Cathedral, which collapsed twice and was never completed. Unfortunately, not much of the frigidarium has survived to the present day, but we can get some sense of its grandeur from a 20th century building, Penn Station in New York City, which was actually modeled on the Baths of Caracalla. Perhaps the most impressive aspect of the structure is the expanse of groined vaulting that forms the ceiling. Now, a groined vault is formed by intersecting 2 barrel vaults at right angles to each other, like this. The use of groined vaulting in ceilings resulted in the subdivision of the interior space into square or rectangular bays when viewed from above. Each transverse vault corresponds to 1 bay. This arrangement was so successful that it was ultimately adopted as one of the fundamental characteristics of both Romanesque and Gothic cathedral architecture 1,000 years later. As we'll see, the beautiful vaulted ceilings like this one at Laon are direct descendants of the Baths of Caracalla. Note also that the groin vaults in the baths and even in these cathedrals allow for larger window openings higher up in the enclosed space, a feature that profoundly affected Gothic architecture and one that was also vitally important to the function of public buildings like the Roman baths and like Penn Station that you see here. Now, like any arch or vault, a groin vault can only remain stable if its lateral thrust is restrained. For massive concrete vaults like those used in the Baths of Caracalla, the thrust would have been immense. Roman engineers met the challenge in 2 ways. First, they lightened the vaults by casting into them a grid of octagonal indentations called coffers, which you can see here in the vaults at Penn Station. The coffers might appear to be purely decorative, but they actually serve a vital structural purpose. In our lecture on arches, we saw that the lateral thrust of an arch is directly proportional to the magnitude of the downward load. Since the largest downward load on these vaults is their own self-weight, reducing the weight of the vaults causes a corresponding reduction in thrust. The second technique that Roman engineers used to restrain the thrust of the vaults was an ingenious system in which smaller lateral barrel vaults were added perpendicular to the central space and used to prevent the central vaults from spreading laterally. This system of buttress vaults, as they're called, required a keen understanding of the flow of forces through a complex three-dimensional structural system. This innovation, yet another indicator of Roman engineering savvy, would be adopted in many future buildings, from Hagia Sophia in Constantinople to Filippo Brunelleschi's Church of Santo Spirito in Florence. You can see an example of these lateral buttress vaults in the ruins of the Basilica of Maxentius in the heart of the Roman Forum. This basilica was built in 310 AD and used essentially the same structural system as the Frigidarium of the Baths of Caracalla, except it was larger. The vaulting over the main hall of this basilica spanned 82 feet and was 118 feet high. This small segment of the structure that remains today is so immense that you might think it's the main hall, but no. These three bays are actually the lateral buttress vaults that stabilized the much larger and taller vaults of the main hall. The scale and sophistication of this structure truly proclaims the glory of Rome, yet it also hints at Rome's demise, as Maxentius, the emperor, was the last emperor before Constantine, his successor, moved the capital of the empire to Constantinople. Fortunately, when the emperor moved to Constantinople, Roman construction expertise accompanied him. And we'll see the happy outcome of that historical event when we examine the Basilica of Hagia Sophia in Constantinople 2 lectures from now. Today we've seen a steady progression in the development of Roman art structures from the simple bridges of the 1st century BC to monumental vaulted public spaces of the 3rd and 4th centuries. The early structures were so well conceived and so well suited to the available structural materials that many of them have survived to this day and are still in use. The long-span bridges and great vaulted halls tested the limits of masonry and concrete construction, but succeeded because their designers had developed a deep understanding of structural behavior. And in every instance, the most important aspect of these structural systems was a well-conceived mechanism for restraining the lateral thrust caused by the arches and vaults under load. After the fall of Rome, much of this know-how would be lost, but over time it would be painstakingly restored and then finally surpassed in the great churches of the Middle Ages. Thank you.